Thank you, Mr. Chairman. Thank you, everyone, for joining for this talk about the separation. At the very beginning, I would like to apologize to you because I will start with some very basic things about voltammetry, but I need this to introduce what we are actually doing and how do we do this decomposition. So first of all, this kind of plot everyone would like to get if he's doing any measurements in voltammetry. And in very high simplification, the current that we are measuring can be expressed as a sum of two subcurrents. One will be faradaic current and the other will be capacitive current. So in my talk, this faradaic current I will show in blue color, and capacitive current I will show in red color. And if the plot is black, it means that that's how it was actually measured. And another thing I would like you to notice is that both of these currents differ actually in these equations by the respect of time. So Faradaic current is 1 over square root of t, and capacitive current is exponent of minus t. So now I go a bit further. So differential voltammetry and square wave voltammetry. When you measure something, this is what you get. But you need to remember that this is actually just the difference between the current at the high potential and at the low potential. And moreover, it's not only difference, it's just the difference of the averages, because we are not using every data point registered by the analyzer. We are just using the average of the last part when the new potential was applied. So what's really going on is analyzer really sees something which is in the top right corner there. So you can see that we are just using less than 50% of what's actually being measured. So we are losing much information and just discard it. So our idea was that we should be able to use this current. So for the purpose of this talk, I will call this part of the diagram, which when the potential is constant and we are just sampling the current, sampling time. This part is usually divided into two parts when we don't measure the current that we measure. So in our experiments, we are measuring current all the time, so during this whole sampling time. And now, how do we actually do this decomposition? So we are doing decomposition by the means of trilinear decomposition. So first we need to build our three-dimensional matrix, which is here. So the height of this matrix is potential. So this is given by the program of our measurement. The width of this matrix is sampling. So this is the current that is flowing with a constant potential. And the depth of this matrix is different objects that we measure. So the one very important thing for this decomposition is that in each of these dimensions, we have to have difference between the things that we are trying to distinguish. So if we are trying to distinguish between capacitive and Faradaic current, in each of these dimensions, we have to differ them somehow. So they are for sure different in the sampling region, because I just showed you that the equations are different. They also different in this potential time, because we have parts when there is Faradaic current and where there isn't Faradaic current. And they have to differ also in these objects. So we need to have just different samples with different concentration of our analytes. So this is our basic approach. So then after the trilinear decomposition, we should get three matrices which are representative for each of these dimensions. And then we have to decide how many factors we would like to extract. So in this case, we would like to extract two factors. One will be representative of Faradaic, and one will be representative of capacitive current. So we have these three matrices, and now we can take just each factor from all of these matrices. So, for example, from each matrix you can take the Faradaic factor. We can multiply them together and get back the signal which is shaped as our original measurements. So then from this signal, we can recreate voltammograms or do whatever we want. So because we'll have this, because we have separated already, so this will be, for example, Faradaic measurement, and this will be result of the capacity of how does this measurement look in capacitive current. So of course, first we try this approach with simulated data. However, it is too simple to actually mathematically distinguish between two mathematical functions. So we moved straight to the experiments because the simulation went too well. So our first experiment was also quite simple. We took a glassy carbon electrode, used ferrocyanide ions with relatively high concentrations and measured DPV or differential pulse voltammograms for 6 different concentrations of ferrocyanide ions. So these are our results. So as you can see here, the shapes are well developed, so there's actually not really much need for any further improvements. However, we wanted to test our methodology. Here you can see how does the signal looks in the sampling domain, so where we show each sample that is being registered by the analyzer, so then we use this to create these voltammograms. When we did this, we tried to decompose this data by the method I showed you before, and first we used method of decomposition which is called alternating slice-wise decomposition, and here are the results. At the top, there is something which according to us is representative of capacitive current, because it is more or less constant during the whole this range of potentials that are being changed. Second thing is it changes in one place when there is change from higher capacitive current to lower. This is the result of very high concentrations of ferrocyanide ions. So we are actually able to depolarize the electrode, so lowering potential changes because of the presence and of the constant oxidation of ferrocyanide ions in this region. And if we look at this plot at the top right, you can see that this actually looks, so this is just zoomed fragment from this zoomed piece of this plot, and this actually looks how we would think that the capacitive current looks. So it's very abruptly goes to the zero. And on the blue you can see what we think is faradaic component. So it's so here is reduction of ferrocyanide. Here is a moment when they are both oxidizing and reducting, and here's only oxidation of ferrocyanide ions. And then the plot also looks well like what we would expect from faradaic current, which is really slowly dropping to zero. So it looks quite good. So then we have this, we can try to recreate the voltammograms using only one of those constants. So this is what was being measured, what we had like straight from the analyzer, and this is what we get from decomposition. So we used our decomposed faradaic current to recreate voltammograms, and this is what we get. So we have on blue faradaic voltammogram, and red is capacitive voltammogram. So you can see that we actually managed to improve our signals registered at this experiment, because we have zero baseline for the voltammetric peaks on our resulting voltammograms. So this was already very encouraging, our first result. So we decided to try something more difficult to do. So we created our second experiment, which was measuring lead concentration on silver electrode in the presence of CTAB. CTAB is cationic surface active species. So we choose low concentration of lead to decrease this depolarization of electrode, and we choose quite high concentration of surface active species, because as our idea was that lead will change the Faradaic current. However, CTAB will change the capacitive current, because this is like generally what people think, that we get absorption of surface active species on the surface of the electrode, and then it changes the width of this double layer, and it therefore changes also the capacity. So that was our general idea. So this is what we measured. So we made three calibrations of lead ion concentration in the presence of 3 different concentrations of CTAB. So first is here, second is here, and third is here, with the increasing concentration of CTAB. So the correlations look really good, and they look like what we expect. The more surface active species we have in our cell, the lower is the sensitivity. So our method is losing sensitivity with the increase of the surface active species. So we use this data and try to decompose it with another algorithm, which is called alternating linear decomposition. And we have result of the capacitive component and Faradaic component. This is for the highest concentrations of lead and no concentration or zero concentration on CTAB. So we have also something which looks like capacitive current, which is constant through a whole measurement and not really decreasing, because we have lower concentration of our depolarizer, which was lead. And we have also very nicely looking faradaic component which only changes into place when there is both oxidation and reduction of lead ions, and also afterwards it's negative. So now when we look at how the signals look like in a very brief region near the peak of the lead, this is how they look when they are zoomed. So at the top row we have capacitive current for different concentrations of CTAB, and at the bottom row we have faradaic current for the different concentrations of CTAB. So for this, we try to fit, for the capacitive current, we tried to fit actually the equation for the capacitive current. The fit was really good. However, there was a problem while fitting this faradaic current equation for this for the signal that we think are from Faraday component. Because of the first few seconds, which actually first milliseconds, which actually don't match to this equation. So from the capacitive component, we are able to calculate tau. Tau is cell time constant, which is the delay between when we apply the potential to the electrode and when actually ions in the solution can experience it. So this tau was about 3 milliseconds. So after 3 milliseconds after we apply the potential, it can be experienced by the ions. So we decided to try to fit our faradaic equation after this 3 milliseconds. So after this 3 milliseconds, you can see that it actually looks like something which can be perfectly described by this equation. And the correlation was really, really good, almost as good as the one for the capacitive component. Another thing that seems quite strange to us is that after first addition of CTEV, the capacitive current decreased, but after subsequent addition or capacitive component stayed constant. The change that were actually the most prominent was in the faradaic component. So you can see that after each addition of CTEV, our calibration, the faradaic component is worse and worse. So this means that this was a bit surprise for us because we were expecting most of the changes in capacitive current. So we wanted to see if we can improve somehow analytically this method with our decomposition of the signals. So on the top row you can see what was measured. So this is a signal directly from the analyzer. We were thinking that maybe if you know that this tau is 3 milliseconds, we can improve the sensitivity by using this tau and selecting the best time to sample the current. So here is another experiment where we sampled the current much earlier, so after 3 milliseconds. So this was sampled after 10, this is sampled after 3. And then we tried another approach when we choose only faradaic component and sampled after 3 milliseconds. So you can see that first of all, the sensitivity is much better when we do the sampling after the tau time, so after 3 milliseconds directly. So the sensitivities are much, much better. However, when we look at this, what's being measured in total current, there you can see that first of all the background shape is really difficult to subtract. The background is really high, so this is analytically less helpful signal. And if you look at just faradaic component, we have zero background, so it's really easy to distinguish. We have better sensitivity and much more helpful analytically. Some final remarks. The measured signals were decomposed in faradaic and capacitive components. Both our decomposition methods turned out to be really helpful. We had a little bit of surprise before because surface active species actually change more faradaic component than a capacitive component. And possible application of this method include improving sensitivity and background shape in the measurements, study of the new electrodes and new materials, and measuring the influence or the external influence on our method. And also one thing I need to remark is that this method requires high level of shielding, because we were really fighting for this signal to be good enough for us to be decomposed. So we needed to really put much effort into shielding our cell from the external influence. However, when we actually managed to do that, we were able to improve this method. So if you want to test this, we have created a web page where you can upload your signals and test your signals using this method of decomposition that I showed you. So you can visit just voltammetry.center. This is open source, so you can see how does it work and what does it do. Thank you very much.
Questions? Yes, please.
How does it compare when you do a simple experiment of recording the voltammogram without the electroactive species, then in the presence of the electroactive species, and just subtract the two recordings?
Well, because in voltammetry you cannot really tell if it's exactly the same experiment. So when you do one experiment and you do next, then you are not sure if the sensitivity of the electrode is the same, if everything works as intended. So this is really difficult to do. Actually, I think without doing any mathematically advanced methods.
Yes.
Thank you for the nice talk. So you also validated the faradaic current with the decomposition of the signal. Did you also try experimentally validate the capacitive effect?
Well, unfortunately, no. We haven't done any further measurements with this.
One more question, please. Yeah.
Only short question. I'm not a specialist in software or in statistics. These methods which you have applied, these are mathematical methods which are in some software which was prepared by you, or it is some general software, the method ASL?
Well, the decomposition methods were applied, they are not developed by me, are just used by me, and however the methodology was developed by me. So this is, everything is publicly available.
So in your papers it's possible to find this method, or where it is possible to find...
Excuse me, can you repeat?
where is possible to find mathematical background of your method? In your papers?
Yes. In our papers, everything is either reference or written directly if it's not short.
Thank you.